All right, so let's start this problem. So we're going to draw the shear force and bending moment diagram for this frame. This is very similar conceptually to the one we just talked about in class. You can see that we've got a pin connection at A and a roller at B, so we will be able to find those reactions with one free body diagram of the whole structure, and I think I'll do that to start. Then we'll have to take it apart here at B and C, and as you can see from the drawing, both of those sections are fixed. So we'll be looking for a horizontal, a vertical, and a moment for all of those. So let's start first with a free body diagram of the whole structure. And just to save some time, I'm going to use the actual drawing as my free body diagram for the reactions instead of redrawing it. So at A, I'm going to assume a force in the X, Y, and X directions. Oops. And then this is D, and I'll call that dy. And then I'll come over here and to make it easier for me, I'll make a concentrated equivalent force for this side load. You can see the height is 12 feet and the load is 3 kips per foot. So that'll be a 36 kip force halfway up. That'll be about 6 feet. That should be enough information on this diagram for me to find my reactions. So we'll start with some moments first. A good place to do that would be at A, since two of our unknowns are, their line of actions are concurrent at A. So we'll do that. So there's my equilibrium statement. And then when I go to do it, let's see what I've got. So summing moments about A, I've got this force and this force. Those both create what kind of moment about A? Positive or negative? With right-hand rule. Negative. So I'll do so that's negative 36 kips. The distance from A to its line of action is 6 feet. And then negative moment created by the 15 kip force. And A, its line of action is 4 feet. And then I have my reaction at dy. What kind of moment does it create? Positive. So I've got a positive moment. The force is dy. And the distance from A to D is 8 feet. So we should be able to find dy. I don't know what that is off the top of my head. 34.4. Anybody else get 34.4? 34.5. Close. Which one is it? Should we just throw a coin? Anybody else trying? 34.5. 34.5? Okay. We'll go by consensus. Okay, so now we can do a couple things. I'll sum forces in the y direction and make sure that's in equilibrium. So there's my statement. So what do we have in the y direction? I'm assuming up is positive, so I have AY up. I have dy also up. And I've got this 15 kips acting down. So since I know dy, I can plug it in here. I should be able to find AY. What's AY going to be? Looks like it's going to be negative. 19.4? Oh, 19.5, sorry. Anybody else get that?
Yes.
So why do you think AY is negative? Well, think about this. If you imagine this structure kind of hinged here at D, and you start pushing on it horizontally, that's a pretty big force compared to this one here. So this structure is probably going to want to rotate clockwise, right? So A is going to have to hold it down. A lot of times you think of foundations being just holding the building up, right? Sometimes it has to hold the building down. So the foundations can be fairly sophisticated. Not only do they support the weight and spread it out into the soil, but they can also use the friction of the soil to keep the building from flying away. And in bad weather, that is an issue. So if you sum forces in the x direction, that's our last thing we need to do. What do we have? Well, all we have is AX. That's to the right, so that's positive. And then I've got my 36 kip force, which is also to the right, so I'll assume that's positive. So now when I solve for AX, it looks like it's negative 36. And that makes sense too. Since the structure is being pushed to the right, the reaction better push back to the left. Okay? So now what do we do? I think we need to start taking this thing apart at B and C. Looking with your experience in looking at the structure, imagine A to B as a free body diagram, a second free body diagram from B to C, and a third from C to D. Which of those three are going to be easier to work? What's going to be the easiest one to do? Probably C to D. There's no loading, just one reaction. That's going to be pretty easy. Now, AB or BC, which one of those is going to be easiest to do? AB. BC is pretty easy too. In fact, they're pretty much the same at this point. So I'm going to start with that kind of strategy. I'm going to start with CD since that's the simplest one to do. So I'm going to come down here and say I've got a free body diagram from C to D. And I'm going to draw that body. There it is. And I'm going to put my dy reaction on it, which was 34.5 kips. And now I'm going to go up here and assume at B that I have an X force and a Y force and a moment. Now, I'm not going to be concerned right now that which are shear forces, which are axial forces, and which are bending moments. Oh, I did the wrong one. That should be C. Yeah, sorry. Thank you. It's going to make my drawing look a little nasty, but maybe I need some maximum energy drink. I should be well rested. I get to actually sleep in this week. My kids are off school, so I don't have to push kids out the house at 6 o'clock and get on the bus anymore. So I got to sleep in until 6:30. Should be well rested. But I need a sugary treat and a big jug of coffee. Oh, I brought my coffee. Hang on a second. I'll let you guys catch up. I'm sure you have to do some erasing. All right, so let's go. So now with these proper labels, let's sum moments at C. And make sure that's in equilibrium. So what do I have there? Well, I have my moment at C. That's positive. And what else? Nothing. So we're done. The moment at C is 0. We can sum forces in the y direction. Make sure it's in equilibrium. So what do we get when we do that? Well, we've got CY acting up, and we've got 34.5 kips acting up also. So it looks like CY is negative 34.5 kips. So with CY actually acting down, you can see this element is being compressed. Right? And then the last one would be to sum forces in the x direction. I think it's going to take us longer to write this equation out than it is to solve it. So when I sum forces in the x direction, what do I have? I have Cx, and that's it. So Cx is 0. So there's my 3 values. Now you could put those on a free body diagram of BC with that information at C and solve that, or you could go to AB. And right now, either one of those looks fine. There is a slight advantage to going to AB in that If I've made a mistake here in these calculations, then they're going to pass on to my calculations for B. If I do AB, my only problem would be if I made mistakes at A. But if I made mistakes at A, I've made mistakes at D, and I'm already going the wrong direction. So it might be safer to get a fresh set, and let's go A to B. So we'll come over here and we'll do the free body diagram from A to B. So I'll draw that one. Now we know at A, we found AY, and AY is actually down 19.5 kips. And we found AX, and it's actually to the left equal to 36 kips. And then we have a horizontal applied force of 3 kips per foot. And then at B, I'm going to assume, let's see if I can get this right, BX, BY, I didn't leave myself a lot of room, right-hand rule, moment of B. Sorry I had to wedge that in there. It's not very pretty. And this thing is 12 feet tall. I forgot the distance over here. We didn't need it, but I'll add it. So just like we did up here, we can use the concentrate equivalent right now for the reactions, which we found to be 36 kips, halfway up, or 6. So with that free body diagram, as crammed in here as it is, we should be able to solve for those reactions. So let's start by summing moments at B. Make sure that's in equilibrium. So looking at this free body, we're going to sum moments about B. Well, you see BX and BY pass through B. They're not going to create any moments. So what is the moment at B? Positive or negative? Positive. This 36 kip equivalent force is going to create what kind of moment about B? Positive. And the moment will be the force, 36 kips, times the distance away, which is 6. What about this 19.5 vertical force? Does it create any moment about B? No. But the horizontal one does. Is that positive or negative about B? Negative. So it'll be a negative moment. That force is 36 kips. And that moment arm is 12 feet. So it looks like the moment at B is going to be 218 kip feet? Negative? I don't know. I'm guessing. 216. Yeah.
Isn't it positive?
Yeah.
What?
It's positive.
Isn't it positive? Should be positive?
You are correct. I saw that negative sign there, and that influenced me, but that needs to go to the other side of the equation. You're right. So there's a big 36 kip force down here in the reaction. That's doing most of the moment about B. This 36 kip has half the moment on it, so that looks good. So what else do we have? We can go ahead and sum forces in the y direction. So in the y direction we have what? We have By acting up and 19.5 acting down. So it looks like that By is equal to 19.5 kips. So in this one, you can see the forces are trying to pull apart. So this element is in tension. So again, as this big horizontal force pushes here, this front column is stretching, going in tension. The back column is compressing as it kind of rocks to the right. And then the last thing we need to do is find the force in the x direction, so we'll sum forces in x. We have bx to the right, so that's positive. We have our concentrated equivalent 36 to the right, so that's positive. And this 36 is to the left, so that's negative. Looks like bx is 0. So now I have all the pieces. So we've been doing this now without my commentary for around 15 minutes. And all we have is now the data to draw the shear force and bending moment diagrams. So these problems are by their nature a lot longer. They're not harder, they just take time to do. Now, one thing we can do right away, do we need to draw a shear force and bending moment diagram for CD? No. There is no shear force, there is no bending moment. That's an easy one to do. So we're just going to focus on AB and BC. And I'll do AB first, and we'll rotate it over on the side. So I'll flip this up, and I'll draw we'll do AB first. So with it rotated over on its side, it looks like this. Now, we'll go back here. So looking at it this way, you can see that the AX force is going to be the shear force at the start. And AX was 36, and it was acting up. See that? Or actually to the left, which is going to be up. So that means I'm going to start my beam with a force acting up of 36 kips. Now what's happening at B? At B would be BX, and we found BX was 0. So there's no shear transferred there. Now let's look at moment. What was the moment at A? Well, it was 0. It was a pin. What was the moment at B?
216.
And we saw for it was 216. You can see it's positive, so it's going to be drawn this way. So that's 216. And on this side, we're going to have a moment of 216 kip feet. So those are the reactions that I'm going to have to deal with. Shear and moment on the left side and shear and moment on the right side. And then, of course, the structure had a uniformly distributed load acting to the left or to the right, which is actually down for us. And that was 12 feet, and this was 3 kips per foot. So now we're ready, with that information, we're ready to draw the shear force and bending moment diagram. So I'll extend a template to help us draw it. There's the beginning and end. I'll establish a positive x-axis, positive shear, and we'll do everything in kips. We're also going to remember that the change in shear between any 2 points is going to be the area under the load diagram, and that the slope of the shear diagram is given by the load. So starting here at A, what's the value of our shear? What's that? Positive or negative shear? Positive. So we're going to start at 36, and we're going to go to a shear of right-hand side, 0. So we see what the change is going to be. What does this say? It says the change in shear is the area under the load curve. What's the area under the load curve? It's a rectangle, base times height, 12 times 3, it's 36. And the load is down, so that's negative. So 36 minus this change, which is also 36, does bring us to 0. So that works great. And then the slope of this moment, or the shear diagram, is given by the load. So the load is always 3, and it's always negative. So we get a constant. In fact, if we wrote it, the slope would be 1 to 3. So there's my shear diagram. All right, so now let's move on and do our moment diagram. So I'll assume a positive x, positive for moment. All my values will be in kip feet. So what do I know about the moment. What's the moment at A? 0. What's the bending moment at B? Well, it's 216. Is this positive or negative bending moment? Positive. Now for the moment diagram, we know the change in moment between any 2 points is the corresponding area under the shear diagram. So let's see what that will give us. So what's the change? What's the area in the shear diagram between A and B? Well, it'd be this triangular area. 1/2 the base, which is 12 feet, times the height, which is 36, which is positive. That's a positive area. Positive 216. So 0 plus 216 is 216. That works. And then the slope of the moment diagram everywhere is given by the shear. So let's look at the shear diagram starting at 0. The shear is positive, big positive value. And it gets smaller and smaller to at B it is 0. So those are my slopes. So if I kind of connect the dots a little bit and the slope, this is what I would have as a rough idea for my moment diagram. So let's now, right next to it, let's do the section from B to C. Now this one isn't as abstract as A to B because I can literally see what B to C looks like, so I'll go ahead and draw that. And right now I know right in the middle I have a 15 kip load, 4 feet and 4 feet. Now what do I have at B? Well, let's go back and look at my drawing. When I did my free body diagram from A to B, I found BX and BY and the moment at B. So this BY force gets transferred to BC as a shear force. So what is BY? We found BY was 19 up, right? So what is it on the other one? If it's up here, it must be down here. Is that right? You guys see that? BY up, and we got a positive value, so it means it's down on the other side. Is that right? I'm not getting a warm and fuzzy feeling from you guys. No? You see that? I can't. Well, maybe I can kind of roll it over there a little bit. No, you can't really see it. What about on this end? This is C, all right? So when we solve for CY over here, what do we get? We got CY was negative 34.5. We assumed it was up, so it's down here. That means it has to be up on the other one. What did I say? 34.5? If you do a quick inspection of this free body diagram with just the forces in the y direction, you can see that 15 plus 19.5 are balanced by the 34.5. So it's still in equilibrium. So we got that right. Now what else do we have? Well, what's the moment at B? Yeah, we found that it was right this direction at B. So on BC it's equal and opposite. So actually it's in this direction. See, when you put those two together, they cancel out. Do I have a moment at C? No. Remember we solved for that previously. And we found the moment at C was 0. So after all that accounting is done, now we have this problem to solve. So there's my template for the dimensions of my beam, and we'll start with the shear force. We'll do that in kips. I kind of jammed it in there. Sorry about that. What kind of shear is this? Kind of hard to see. Is that positive or negative shear, this 19.5? It's acting down on the left side. That's negative. So I'm going to start off at negative 19.5. What kind of shear force is this? Up on the right-hand side. That's also negative. So there's my 2 points. I've also got this point load, so I'm going to add that to my template. So now looking at the change in shear between any 2 points is given by the load diagram. What's the load over the first 4 feet? 0. So there is no change. So if I start at negative 19.5, I'm going to stay there. And of course, the slope of that curve is given by the load. The load is 0, so 0 slope. So constant shear over the first 4 feet. Then as I go from the left side to the right side past this applied force, how does my shear change? It changes this amount, 15 kips. Is that negative or positive? Negative. So that should bring me down to negative 34.5. Now the change in shear is the area of this part of the load. If I look at this last 4 feet, again, no load, so no change, and you can see the two match. And of course, then the shape of the shear diagram is the load. And the load is 0, so 0 slope. So now you have a nice little kind of step diagram for the shear. Let's draw the moment. I'll assume positive value for x, and the moment, we'll make this in kip feet. So what is the bending moment at A? What is this bending moment? Positive or negative? That's a positive bending moment, so it's going to start at 216. What's the bending moment at C? 0. I got to make those two connect. So the change in moment is the area of the shear diagram. So the change in moment over the first 4 feet would be this given by this moment, this shear diagram, which is 19.5 times 4. What's that? What is it?
Goes down to like,
And then you subtract that from 216. What do you get?
goes down to like 139.
139. And then what's the slope of the moment diagram? Well, it's equal to the shear. And if you look up the shear value, it's constant and negative. This is not to scale, but you can see that the slope of this line would be negative 19.5. Now the change in moment from 4 to 8 feet is given by this part of the shear diagram. I'll double hatch that so you can see it a little better. And what is that area? Well, it's 4 feet times negative 34.5. Hopefully that's 139.
It should be 138.
138. Okay. Does that get you to 0? It does. And then, of course, the slope of this line is given by the load. You can see the load is constant and negative, and a steeper slope. So you do get a little bit of a bend in it. So there's your moment diagram. So what is the slope of the moment diagram at A, or at the beginning, which would be B? It would be negative 19.5. What's the slope of the moment diagram at C? It should be here, negative 34.5. You can read all the answers you need right off the diagram. Okay, that was long. That was 29 minutes long. So quite a tedious problem.